I'm delighted to be here to welcome Paweł Świeboda, founder and director of Neuroscience, practice lead for neurotechnology, International Centre for Future Generations, senior visiting fellow, European Policy Centre, senior advisor on brain health, FIPRA, member of the steering committee, Brain Capital Lab. It's great to have that opportunity to hear you speak at the Brain Summit at the Champalimon Foundation in Lisbon last month, Paweł, and we're really grateful to have you here to take a deeper dive into your thoughts regarding neuroscience, the future innovation insights from the Human Brain Project, and reflect on AI and neuroscience and how they should relate to each other. As we explore your insights from the Human Brain Project, could you explain what was the core mission of the Human Brain Project?
Thank you so much, Amanda, first of all, for having me today. Delighted to talk and reflect a bit about the achievements of the Human Brain Project, which was, just to explain to those of our viewers and listeners who might not have followed this project, this was a European flagship program that lasted for 10 years. Started in 2013 and just ended in September, so quite recently. And it was a basic science project focused on better understanding of the brain, better understanding of the human multiscale connectome in particular, and problems of cognition and consciousness, some of the fundamental challenges to neuroscience. And when I say a basic science project, that doesn't mean that it hasn't focused on how that knowledge could be applied in practice. There is, in fact, quite a lot that is gone out of the project to impact on practical applications in brain medicine, in particular in brain-derived technology. But in its essence, it was a fundamental science project. And what's so special about it is that when it was launched over 10 years ago, the idea was to basically use the newly emerging computational capabilities to try to understand the human multiscale connectome better. And that had not been possible before, obviously, and there had been massive technological progress, which the Human Brain Project both benefited from and contributed towards. And just to give you an illustration, I mean, there were scientists in the Human Brain Project who remembered working with single neurons. And there is nothing wrong with working with single neurons. One has to do that, by the way. But there was simply no other means. Namely, it was not possible to do anything else. While today, it is possible to study entire populations of millions of neurons in different locations of the brain and over the duration of long behaviors. So this is a revolutionary change in terms of the means to understand the brain. And of course, the means are the means, meaning they have to be applied to develop principles and maybe in the future also a theory of the brain. There is a discussion about that, whether we will have a uniform theory of the brain. I think the consensus view is more that we will have a set of principles rather than a single theory. But definitely progress is being made. So decoding of the brain, that's one fundamental challenge. Also studying cognition and consciousness, and this has led to some very interesting developments. Consciousness is one of these sort of holy grail challenges for neuroscience. What was possible in the Human Brain Project was to develop also a way of measuring consciousness. And this has very direct practical application for treating especially deep coma patients. What it turns out to be the case is that about 20% of those deep coma patients have the level of consciousness which is very similar to the one that the two of us have and that people who are in perfectly good shape have. What the Human Brain Project worked out is a way of calculating that, measuring consciousness. You could call this a consciousness meter. It's the concept is called the perturbational complexity index, and it allows you to be able to know a little bit better what could happen and whether or not you could double your efforts to bring someone back to life who is in a deep coma situation. So these are some of the examples of what the Human Brain Project delivered. A lot of the work will be relevant for years to come. I would say one example is the groundwork that has been done in the area of neurotechnology, especially when the different computational models are concerned. So when you look at the breakthroughs which are emerging from many labs around Europe at the moment, for example, the work on spinal cord implants in EPFL in Lausanne, in Switzerland, the groundwork for this was done in the Human Brain Project through the computational modeling. And today, the result is phenomenal. There are already patients who were able to walk again, having suffered paralysis within 24 hours of having such spinal cord implants being inserted. So a lot in the area of better understanding of the human multiscale connectome, but also a lot in terms of what this means for applied brain medicine.
Forward now, there's obviously a lot of focus on AI and the intersection of that within neuroscience. Could you just tell us a little bit more about that intersection within the field of neuroscience as it relates to the Human Brain Project?
So when it comes to this intersection or relationship between neuroscience and AI, well, it goes back quite a number of years, and there is an ongoing debate about this, and I hope that we will have the time to come back to this a little bit later. But specifically within the Human Brain Project, the situation was twofold. On the one hand, the brain researchers working in the HBP were big consumers of AI developments and AI advancements, and they also contributed to developing more, I would say, brain-inspired or brain-derived AI algorithms. And let me say a few words about each of these categories. So the complexity of brain science is immense, and just to illustrate, when the Human Genome Project was successfully concluded, I mean, this was about decoding 20,000 of the genes. And now in the human brain, there are 86 billion neurons, each with thousands of connections. So if you multiply one by the other, you get the picture of the scale of the phenomenon. It is, in terms of the scientific endeavors, it really comes on par with studying the universe. There's nothing more complex than this. So what this means for AI is that obviously brain science must be a big consumer of AI algorithms, because in order to make sense of the big data coming out of the newer methods of studying the brain, you need those algorithms. And in the Human Brain Project, we developed something that was eventually called the EBRAINS knowledge loop. EBRAINS, because EBRAINS is the research infrastructure that Human Brain Project worked out, and it is out there to serve the community. And the knowledge loop is really about taking the empirical data that you can have on the brain of each individual patient, adding the reference data coming, for example, from brain atlases, because the challenge of studying the brain is its inaccessibility. It's very difficult to get to the tissue in the brain. And when you look at what really contributed to breakthroughs in oncology, it is molecular biology, meaning getting down to the tissue. Well, in the case of the brain, I think a similar trajectory is very much important, but it's just so much more difficult because the brain is enormously inaccessible. So you add to this empirical data also the reference data coming from brain atlases. You do modeling and model validation. And then you also throw the AI algorithms to try to draw insights from that existing and simulated data. And this is what produces new knowledge. Human Brain Project and brain research in general is a very strong demandeur for new AI methods, but it also contributes to the development of AI. And one example that I would like to give is the example of so-called learning algorithms. So these are the AI algorithms which try to draw insights from the way the brain functions. And the brain is very effective in the way it operates. So it takes from the memory what it needs, as opposed to the microprocessors, which still take everything that they need and then throw everything back. So the brain is more selective. It really identifies what it needs, and this is, at the end of the day, much more efficient. So these learning algorithms are one example of new AI methods that the Human Brain Project contributed to. I think there are two fundamental issues when it comes to neuroscience and AI. And again, the debate on this is ongoing. There are many points of view, but let me focus on the two that I want to share, namely, first of all, drawing on what I said before on these brain inspired algorithms, the learning algorithms. I think what they achieve, and which is enormously important, is greater energy efficiency as well. And we desperately need that because the way AI develops at the moment is by scaling up the availability of data and drawing insights from it. But clearly, this method is not sustainable in the longer term because the energy bill for the continued use of AI along these trajectories is simply going to be too high for, well, the planetary boundaries to pay for. So this is one example of an area where insights from the functioning of the brain are desperately needed. The second area is to really define what it is that AI should achieve. I think AI has been obviously enormously successful in its rather basic function, which is based on pattern recognition. It's the result is spectacular. There is no question about that. But if we want to move towards human-like intelligence, then the question becomes how to define the problem, and this is where brain science can help. I mean, what are the success criteria for human-like intelligence? I think this is where the study of the brain, so cognitive science, neuroscience, also psychology, can be extremely helpful. So learning more about the memory systems of the brain, the use of language, the task-related control. This will take us into the territory of defining better what are the areas that human-like artificial intelligence should focus upon. So something needs to happen, and the methods needs to change. One way of drawing inspiration from the brain is to look at its selection modes and the energy efficiency that flows from it. But maybe a third area that I would highlight is what is happening in brain medicine at the moment. And I think we have an entirely new period at hand at the moment with respect to breakthroughs in brain medicine. They have to do with some of the new drug design methods where AI algorithms are, of course, increasingly essential. And they also have to do with neurotechnology. Neurotechnology is an important part of the picture because not all the brain disorders can be treated in a pharmacological fashion. In many cases, you simply do not have pharmacological approaches that work, and neurotechnology provides solutions. But again, in order for that to be as precise as we want neurotechnology to be, AI methods are essential, and they are already behind some of the most important breakthroughs happening right now in, for example, overcoming visual impairment or overcoming mobility impairments. I think we are at an inflection point with respect to the growth of neurotechnology, and AI will be part and parcel of that.
Yes, absolutely, and such welcome news to many, many people and many families. And it's great to see how this expansion is being accepted within the scientific community. So you've done some incredible work, and you're working with some incredible partners, and you're making great strides. Can you discuss any innovative projects or technologies within the field that you're currently developing now or planning to do so in the future?
Well, I'm currently working on the policy and ecosystem solution context for brain health. So what I'm focusing on is to make sure that the breakthroughs coming out of research fall on fertile ground with respect to the policy environment. I mean, let's take the example of the molecules which are now gradually being approved for the treatment of Alzheimer's disease. We had Biogen's molecule approved in the United States in June. There is another one by Eli Lilly, which is in the process. These are infusion-based treatments, so that means that patients need to go to a point of care and get the medication applied there. They need to be monitored as well for comorbidities. So what it really means is that one needs to develop an entire new system of care in neurology, which is somewhat alike the system that was developed in oncology, where we also have infusion-based treatments that are at the heart of the therapeutic approaches. So the development of that care system is of essence, because we cannot afford to waste any time given how important these new medications are. Another important dimension is the emergence of new biomarkers and often blood-based biomarkers, which means that they could be also applied in primary care. That will determine many years before symptoms appear that a disorder is already in progression. Now, how do we prepare the health systems for this is a big challenge, and that I think is an essential component of addressing brain health needs today, and this is what I'm focusing on in the current period.
Well, best of luck with that. That's an important and essential role. I don't think there's probably anyone better than you to be doing that. Thank you so much for sharing your time today, for your insights. It's hugely inspirational to listen to you speak and to know that there are all these great things happening out there in the name of brain health. So thank you so much.
Thank you so much for having me, Amanda.
Speaking to you again soon. Take care. Bye.
Many thanks.